we get started, I would like to take this opportunity to say Eid Mubarak for all of my Muslim students, as well as I wish everybody, all of you guys, are enjoying this beautiful weather and keeping it safe. Today, we will finish together the whole content of Module 2. So let's get started. So previously, we have covered most of the Boolean algebraic postulates as well as theorems that used to simplify any Boolean expression. One of the most important algebraic laws is called DeMorgan's. The first DeMorgan law stipulates that the complement of the sum is equal to the products of the complements. So what do I mean by that? So if I have two inputs and I OR them together, then I complement the resultant in Z. That is equal to if I inverted X and inverted Y and then adding them together. Okay? So to prove that, I have here like function Z has two variables. So I have a truth table with 4 possibilities. In order to find X plus Y, it's simply an OR gate between two inputs. So I will get 0, 1, 1, and 1. Then after that, what I'm going to do is I'm going to complement this by just inverting each value at each row. Okay, so 0 will become 1, 1 will become 0, and 1 will become 0, and 1 will become 0. Now, if I do the same when it comes to computing the product of the complements and I get the same, that means that the DeMorgan law is proven. So if I need to find the complement of X, so what I have to do here, I will simply need to look at X and complement each bit accordingly. So the 0 here will become 1, and the 1 will become and the 0 will become 1, and for the 1 1 it will become 0 and 0. Okay, and for Y what I have to do the same. So to find Y prime, I will have 1 because this is 0. I will have 0, then I will have 1, and then I will have 0. And at the end, both of them should be AND. So if I AND 1 and 1, I will get 1. If I AND 1 and 0, I will get 0. 1 and 0, I will get 0. 0 and 0, I will get 1. So as you can see, guys, this column is equal to this column. That means that the complement of the sum is certainly equal to the products of the complement. When it comes to the second DeMorgan law, it's actually the opposite. So the complement of the product is equal to the sum of the complement. So if I have two variables, X and Y, ANDed, and the resultant is inverted, that is equal to if I have to invert each input individually, then OR them together. To prove it again, we will do the same by going to the truth table, and apparently, as you can see, guys, here I have this is equal to this at all possibilities. As such, the second DeMorgan law is proven. But why do I need to know about the DeMorgan law? What is the benefits from interchanging the AND to OR and so on? The benefit from that is I will introduce a new type of logic gates. Those types are called the NOR and the NAND gates. Okay, and the symbol for the NOR is simply like an OR with just a bubble at the end, and the symbol for the AND is for the NAND is like an AND here with a bubble at the end. Those NOR and NAND gate are said to be functionally complete. Why? Because they can be exclusively used to implement all three of the fundamental logic gates, the AND, the OR, and the NOT. Okay? So, in general, guys, it is easier to build digital circuit using NAND solution or NOR solution than combining the AND with the OR with the NOT. An example from a real life is that when you want to buy an SSD, all SSDs are implemented with NAND only. Why? Because it's cheaper to implement the whole digital circuit with just one type of gates. Therefore, both NAND and NOR are called universal logic gates, as any digital circuit can be designed by just using these gates. So let me show you here. Now, let's take a look at the NAND again. Okay, I can implement an inverter with an AND only by A and A, so both of them are prime, are equal to A prime. So basically, I was capable to implement an inverter with NAND only. A NAND gate whose output is complemented is equivalent to an AND gate. So basically here I have an AND gate, okay, and this will give me A, B prime. And what I have to do is to apply what I learned here to implement the inverter using an AND. So again, I will NAND the resultant with itself. So I will get A, B prime prime, which is equal to AB. Okay? Now, when it comes to implementing an OR using an AND solution, so an AND with the complement inputs act as an OR gate. So what you have to do is we can use the first DeMorgan law in order to implement an OR using NAND only solution. In other words, this is an inverter, so this will give you A prime, and this is an inverter, this will give you B prime. And then what I have here, I have A prime and B prime. All of them are going to an AND. So what I can do, I can bring the prime in, so what I will have, and then I should change the sign. So this will be equal to A double prime plus B double prime, and that is equal to A plus B. Okay, so as a matter of fact, most integrated chips, or what is referred to as ICs, are implemented exclusively via NAND only or NOR only. In general, ICs can be classified using the family of the transistor used to implement them. For instance, I will have the bipolar transistor logic, or the emitter coupled logic, okay? Or if you remember when I showed you how we implemented the NOT gate using both P and N type metal oxide semiconductor, okay? In addition to that, integrated circuits are sometimes grouped by manufacturers as their circuit complexity. So maybe like you heard about, VLSI. So VLSI stands for very large scale integration. It's how many gates I have on that chip. So this chip here, this black chip, has millions of a NAND only or a NOR only solution. So let me show you an implementation for that. So let's suppose that we have a chip with only like 4 gates, okay? And we would like to use these ICs in order to implement a digital circuit like using the commercial. So let me explain it more further. If I need to implement this simple Boolean expression using the commercial ICs available in the market. So I have I have an IC with the component number 74LS06, and I have another IC here. The component number of it is 74LS32. So in order to implement this digital circuit, I will need two different type of ICs. However, I can implement that circuit by using a NAND only. Just remember, a NAND gate whose output is complemented is equivalent to an AND gate. As such, those IC for an AND can be replaced with an IC with an AND. On the other hand, an AND gate with complemented inputs act as an OR gate. As such, the OR gate at this Boolean expression X can be replaced by gates number 5, 6, and 7. And since we can eliminate the double inversion for 3, 5, and 4, and 6, the whole circuit can be implemented with just one IC. NOR gate, which is also said to be a functionally complete gate. So in order to implement the inverter using a NOR gate, what I have to do is to NOR the input with itself. So if A plus A, both are NORed, so A plus A will give you what? A, so this will be an A prime. Now, what about implementing an OR using an OR gate? So an OR gate whose output is complemented is equivalent to an OR gate. So basically what I have to do first is to implement an OR. Then after that, I should apply the double prime. So I will take over this prime. So I will get here A plus B. An OR gate with the complemented inputs act as a NAND gate. So what I have to do in order to implement a NAND gate is to complement A using what I learned here, okay? And after that, complement B. Then after that, what I have to do is to NOR the complement of A and the complement of B. This is F function F. Function F will have A prime plus B prime. The whole expression is a prime. So if I take the bigger prime, what I have to do is to change the sign. So this will become A, B, and double prime, and this is apparently equal to A plus A and B, okay? So at any given times, DeMorgan rules are important because they allow conversion to NOR representation. Okay, guys? In summary, so let's suppose that we have an n Boolean variables. I can interchangeably change the operation from OR to AND by distributing the complement to each term inside the parentheses. So let me give you an example here from an old exam. So suppose that we have a Boolean expression function f, and you are supposed to implement it using the fundamental logic gates, which are the AND, the OR, and the inverter. And then you need to implement function f with an AND logic circuit only. So how can we do that? So basically, first of all, let's implement this function using the AND OR. I have here A, and I have B, both of them are ANDed. Then I have C, which is inverted, and I have D, and I have E. Both of them are ANDed. Okay, so then after that, what I have to do is OR all of these results. Okay, and that is function F. So I can implement this function by applying the DeMorgan law, which is like DeMorgan states that F equal A B plus C prime plus D E, and I can take the double prime for this, the double prime for this. Then after that, I have to go and change the operation between each of the terms. Okay, so this will become, if I make it down, if I take the complement here to each term here, so I will have A, B, both are primed. Then this will become an AND because I brought that prime, and then I have C double prime. Then I will have here again D E prime. Okay, and I have the all of that expression primes. So what I can do, like this is an AND, and this is a NAND, and this is an AND. Okay, however, I have, and the output of each correspondent terms is NAND with the gate with 3 inputs. However, I have like a shortcut method that I would like to share it with you. So if you already implement your Boolean expression using using the AND OR logic circuit, you can follow the following steps in order to implement the function with an AND only solution. So how that function can be implemented: first, you have to place a bubble at the output of each AND gate. So I have to place a bubble here, then I have to place a bubble here, and then I have to place a bubble at the input of each OR gate. So a bubble here, a bubble here, a bubble here. As a matter of fact, like this is a double inversion, so I'm not doing anything. And then I have to check the logic gates on the lines coming from input and going to the output. So basically, this has to be what? Has to be like, if this is will become like C, this is a prime, and this is a double prime, so I will get C prime. So what I have to do, I have to ignore this. So this will be equal to A, B, NANDed together, and C just by itself, and then I have D and E, both of them are NANDed. And this, remember guys, so let's suppose that this is X and this is Y and this is Z. So, and since X here, X, as you can see guys, is inverted because of this bubble, so, and Y is inverted because of this bubble, and Z is inverted because of this bubble. So, and all of them are ORed. So I have here X plus Y, X prime plus Y prime plus Z prime. So this can be easily rewritten using DeMorgan by changing the operation X multiplied by Y multiplied by Z, all of it complemented. So this is basically a NAND gate. Okay, so this gate can be replaced by an AND. For function G, I can do the same. So either I'm gonna follow the second DeMorgan law, or I can use the shortcut. So let's try both of the solutions. Now, using the second DeMorgan law, I should say that G double prime, okay, is equal to this is double prime, okay? And now this G can be rewritten as what I have to do now. I have to change the sign, the operation here from AND to OR, and this is to OR. So, and then divide the complement on every term that I have. So it will be A plus B complement plus C prime prime plus D plus E, okay? And this is a prime, and the whole thing is complemented. Now, this is apparently, I will keep it the same like this. I will keep A plus B to be complemented because that's basically an OR. And for this gentleman, C will be equal, like C double prime will be equal to C plus D plus E, and this is also an OR gate, and the whole term is complemented. So that is what, guys? That is an OR. Okay, so basically for when it comes to the C, I don't need to do anything. Okay, now I can follow the steps for doing it without thinking. Okay, so what I have to do first, I have to draw the implementation of function G using the fundamental and or logic circuit. So I have A and B, okay? So both of them are ORed, okay? And I have C prime, so C is inverted. And I have here D and E here. Both of them are ORed with each other, okay? So what I can do now is AND the whole term to get function G. Now, so after I draw the implementation of function G, I should place a bubble. So after I draw the implementation of function G, I'm gonna place a bubble at each input to the AND gate. So here I have an AND gate, so I'm gonna like and a bubble here, and then a bubble here. When it comes to the OR, I'm gonna place a bubble at the output of each OR gate. So here I'm gonna place a bubble, and here I'm gonna place a bubble. And after that, I have to check the logic level on lines coming from inputs and going to the output. So basically, I have to pay attention to C because C is, here it will be like C prime, and then C prime, I have to have it like this. So what I have to do is to pay attention to this one. Okay, so to remove it. Now, what I have to, now this logic diagram is basically an OR, and this one is basically an OR, and this one is a literal, so itself, so it's gonna be C. Now, when it comes to this one, let's assume that this A plus B prime is equal to X, and this is C itself, and this is equal to W. So what, like function G is basically equal to, now X is what here is inverted, okay? So since X is inverted, so what I have X here, and it's inverted, and this is ANDed because that's an AND, okay? C, okay? As well as that is W inverted, okay? Now the C can be rewritten as a double prime here because that will not harm me. And this, according to the second DeMorgan, can be, I can take the complement and change the sign, change the operation. So this will be X plus C, yeah, plus W, okay? And then I have to take just one of them. So this will be just X, this will be C prime, and this will be just W, all of it inverted. So this is basically what a NOR gate, okay, with a 3 input, okay? So that's, guys, how can I implement any logical function using a NAND only solution or a NOR only solution, okay? Another important logic gate is the exclusive or simply can be pronounced as the XOR. So the XOR gives a output of 1 when the number of inputs is odd, okay? So the XOR operates as an inequality operation, okay? So if the inputs are equal to each other, the output will be 0. If the inputs are different to each other, the output will be 1, okay? The standard symbol for the XOR is like this, and we can refer to the exclusive OR operation by adding a plus and a circle all around that plus sign, okay? So the exclusive OR can be rewritten here uh, in terms of and OR by x y prime plus x prime y. What does that mean? That the output will be equal to 1 as long as the two variables are different than each other, okay? So if x equal to 1 or y equal to 1, but not both of them, then the output will be equal to 1, okay? Now, guys, if I XOR the variable with 0, I'm gonna get the variable. If I XOR the variable with 1, I'm gonna complement the variable, okay? Because at that time, I have, let's suppose that my variable is equal to x here, and I have 1, so I have 0 and 1. So what I have to, oh, okay, 0 and 1, and here I have 1 and 1. So the output is 0 and 1, they're different, so I'm gonna get 1, and 1 and 1, they're equal, so I'm gonna get 0. So I have 1 0 for my output. Let's suppose this is like f, okay? So f, if I compare it to x here, so here if it was 0, it's gonna be 1, and if it has 1, it's gonna be 0. So that's basically an inversion version of x, okay? Now, as an exercise, and I will not post it as a quiz on Brightspace, I want you to prove all the others, okay? The exclusive OR logical operation is a commutative, is following the commutative law. So x XOR with y is equal to y XOR with x. And also the XOR is an associative operation. In other words, here, if I have x XOR with y, then the result is XOR with z. That is equal to y XOR with z first, then the result is XORed with x, okay? As a matter of fact, all of them, even though we have the parenthesis here, all of them, they have the same priority, okay? So guys, as an exercise again, as an exercise here, what I want you to do, guys, is to prove all of these operation, okay? Please, exercise. That is an exercise. Okay? Now, I want to make sure that the XOR can follow the complement law. So, X exclusive OR with Y, all of it complemented. What does it equal? It's equal to complement one of the variable and you will get the same results. So if I just complement Y, I'm gonna get the same result as if I complement the whole term. Or if I complemented X and XOR it with Y, I'm gonna get the same result. Now to prove it, guys, you have to use the truth table. Okay, so let's suppose that like this is equal to like an f function f here. And what we have to do is we have two variables. So 2 to the power 2 equal to 4. And that's it. I have 4 possibilities from 0 to 3. So here I have x and here I have x and y. And this is x prime. So it's basically you need just to flip the bits at x, so 1 1 0 0. Y prime, it will be 1 0 1 0. So y exclusive or with x here is basically what you have to do is the inequality. So it will be 1 here at this case, and 1 at this case, and 0 here, and 0 here. So 0 1 1 0. Then if you need to complement that, you just need to complement the entries at this column. So 0 1 1 0 1 0 and 0 and 1. Okay, now what about if I want to do the exclusive or between the variable, the uh, the actual values of x with the complement of y? So I have to do here, I have to exclusive or this with this one. Okay, so let's compare. This is 0 and this is 1. So since they are different, then the answer should be 1. Okay, and this is 0 and this is 0, so it should be 0. Okay, and 1 and 1. Okay, they're equal to each other, so it's going to be 0. And 1 and 0, they're different, then the answer is 1. If I apply the same, and this time I exclusive or those two variables, I'm gonna get the column here and they're equal to each other. Apparently, as you can see, this is equal to this and it is equal to this. Okay, if we want to prove it using the algebraic proof, so what I have to do is x exclusive or with y, and you remember how we can rewrite it. So that's basically x exclusive x y prime plus x prime y, and all of the whole terms are complemented. Now I can use DeMorgan to insert this complement to each term here. So what will happen is when I apply it here, so I can change the sign or the operation from and from or to and. Okay, and then this whole terms will be complemented and this whole term will be complemented. Then after that, what I can do is insert the complement for each of the term inside the literal of each term. So that's what will happen. So when I apply this here, what will happen is the x and y prime will become x prime, okay, so plus y, okay, and for this one it will become x plus y prime. Okay, then after that I can do just like a simple multiplication. So x multiplied by x prime, this will give you apparently like 0, and this will be like x prime y prime, and this will give you 0 plus x y. Okay, so guys, this x plus like x exclusive OR with y, all of it complemented, will be equal to x y plus x prime y prime. And as a matter of fact, that is also a new type of gates and is referred to as an exclusive NOR. Okay, so let me show you here. So the exclusive NOR is an equivalence gate. Okay, so how it's an equivalence gate? So if the variable x is equal to the variable y, the output will be 1 at all time. Otherwise, it's gonna be 0. So it's the opposite of the exclusive OR that we just studied. Okay, so as you can see here, 0 with 0 will give me 1. 0 with 1, they're different, so it will be 0. 1 with 0, they're different, they will give me 0. 1 with 1, they're equal to each other and will give me 1 here. Okay, so the XOR logical operation can be described either by the equality here, or by negating the XOR, or by having this symbol. Okay, the conventional representation of the XNOR is basically like an XOR with a bubble at the end. Okay, here guys, I would like to share with you an effective technique to get a variable by itself. So if you XOR the variable with another variable and then XOR the resultant with that variable, again you will get the first variable. Okay, so if I XOR x with y, then XOR the result with just y, okay, so what will happen? I'm gonna get x. Okay, and if I XOR x with y and then XOR the result with x, I'm gonna get y. You know why? Guys, remember that the exclusive OR is an inequality. So here, what will happen is when I exclusive the resultant here with y, basically I'm gonna remove y from any component of that term. Okay, so if you would like to prove it, we can follow the truth table. So I have here x and y. So the exclusive OR with x and y is 0, 1, 1, 0. And if and I refer to it as an x1. So what I have to do, I have to XOR x1 with y first and see if I'm gonna get something equal to what? To x. So look at this. What will happen here at y1? As you can see, I'm getting 0, 1, 1, 0, 0, 1, 1. So that is equal to x. Okay. And if I XOR this x1 with x, what I'm supposed to get? I'm supposed to get 0, 1, 0, 1. So 0, 1, 0, 1 at all possibility is equal to here to y, and therefore I'm getting y. Okay, if we want to prove it using the algebraic proof, so x XOR with y, I can rewrite it using its logical operation. So xy prime plus x prime y, and then the whole term will be XORed with y again. So basically what I have to do is I have to keep this term at the base format, then negate y or complement y, and then after that I have to complement the whole thing here and keep y, as you can see that. So after that I can distribute the y for each term inside. So I have here x, y, y, y prime, and here I have x, y, y, y prime. And here, guys, here what I did is I used the DeMorgan in order to change the operation from OR to AND, okay? And then I get the complement inside. Therefore, the whole thing here will become what? will become complemented, and the whole term of x prime y will be complemented, and I will multiply it with y. Then I have to see that this will give me 0 for sure, and this, like y prime multiplied with y prime, this is still equal to what? To y prime, so xy prime. And for this thing, what I can do is I can further take the complement inside. So when I take this complement inside here, when I take the complement inside, I have to change it from and to or, and here from and to or, then remove the complement and apply it for this, and apply it for this. So this will be x prime ORed with y, and this is an AND. You see that this is an AND operation. Multiply with, this will become x double prime, so it will be x, and then this will become y prime, multiply with y. Now it's the time to multiply everything with y again. So when I do so, I will have here y multiplied by x, okay, multiplied by x prime, and x prime y prime y plus x y y plus y y prime y. So this will be equal to, will give you 0, and this will give you 0 for sure, okay, and this will give you 0. So I will end up with having just x y prime plus xy, and the others will be zeros. Now what is the common factor here? X will be a common factor, so it will be x, and y prime plus y, this will be apparently like this, will be apparently 1, so the answer will be x. Okay, this is a question from last year final. So I asked the students to express the complement of the function to its simplicity or simplified form. So what I have to do is I have to use DeMorgan. So DeMorgan here, it's like, you know, it's crystal clear that I can say that this is f prime. Okay, so I just will apply just one prime here because I need to get just f prime, and this, the whole thing will be prime. Then after that, what I have to do is, you know, since I'm applying the f prime, I will take that complement and change the operation from and here to plus, and this will be plus as well, and then I will apply the complement for each one of them. So this will become y prime, and this will become x prime, and the whole term here will be complemented. Okay, then after that, what I can do is change this from an or to and by applying what's called double prime. You know, so I can basically here, to get that, you can assume that this is a double prime. Okay, so you will take the prime, the first prime, and distribute it to each term. So this will become multiply, which is an and I have to apply the complement to each one of them. So this will be complemented, the whole term will be complemented, and this, the whole term will be complemented. Okay, now after that, what I can do, because I can take this complement, okay, and apply it. Okay, so what will happen is when I like take this complement and apply it, what will be, this will be equal to y plus z prime, okay, multiply by y prime plus z, okay, and then after that I can simply multiply both of them, okay, and when I multiply both of them with each other, this will give me 0, this will give me 0, and this will give me what? So this will give me y plus x prime plus yz plus y prime z prime. So this reminds you of what, guys? So basically this should remind you with an exclusive NOR. So this can be further rewritten as y prime plus x prime plus y exclusive or exclusive NOR, sorry, with z. Okay. Okay, guys, here is Granny, and she wants me to share another effective simplification theorem, which is the consensus theorem, and can be called the redundancy theorem. So, the redundancy theorem should be applied if you have three variables, okay? And each variable is, or its complement is repeated twice, okay? So one variable must present in the complemented form. So in my example here, let's take a look here in my example. I have three variables, A, B, and C. One of them, which is C, is what? Is appearing both at the complement and at the base format, okay? So since I have A, B, and C, all are repeated twice, as well as the variable C is presented in the complemented form, the whole condition of the redundancy theorem is satisfied. So what I can do, the terms containing the complement variables, which is in my case C, I should keep it and omit the redundancy term, okay? So in other words, if you have a function that has three variables, those variables repeated twice, and you have one variable that is repeated as itself and its complement, you should just take the one with the complement and throw the redundant term, okay? So f here is equal to f simplified here, and that redundant term can be omitted, okay? So to prove this theorem here, what I can do is I can say that x, y plus x prime z plus y z, it will be equal to xy plus x prime z plus 1 multiplied by yz. If I add 1 here, it will not harm. Then after that, this one, I can rewrite it in a way that will give me an x here, okay? So how to do so? So this one can be achieved by saying that is x plus x prime, okay? Then after that, I will multiply yz with x prime and x, okay? So I have xy plus xz plus xyz plus x prime yz. And then after I rearrange them, okay, I can take xy here as a common factor, and this I will get 1 plus z. And I can take x prime z, okay, and I will get 1 plus y, okay? And this will give me 1, this will give me 1. So at the end, I will have xy plus x prime z. In other words, my function, let's suppose that this is function g, okay, used to have three terms, okay, and has like three variables. Each one of them is repeated twice, where x is repeated as a complement format as well as the true format, and y and z are repeated just as the true format, okay? So what will happen is I can neglect that part, okay? So that is equal to xy here, as you can see, xy plus x prime z, okay? So guys, another information that I would like to share with you is, in general, when it comes to digital circuits, they can be described using the positive logic and the negative logic. When we describe a circuit using the positive logic, the high voltage will be representing the one, and or the true format, as well as the lower voltage, which is 0 voltage, or the ground, will represent what? 0. And the negative logic here is basically what I'm doing is I am taking the opposite. So the higher voltage will be represented by a 0 logic, and the lower voltage will be represented by a 1 logic. That's very important, guys, to describe any circuit by its true function as well as by its complement function, okay? And because we can use that, we can come up with a standard way to describe and write the operation of any digital circuit, okay, as well as Boolean functions. Those two formats, they're called the standard sum of products and the standard product of sums. So it's the SOP and the PoS. When it comes to the sum of products, you have to make sure that your function is described by a sum of multiplications, okay? And all the products are formed by a single variables only. What does that mean? That means in my case here, that is not an example of a sum of product because that is like more than one variable, okay? So each product in the sum of products form is called a min term, though the form is called also a sum of min terms, okay? When it comes to the product of sums, similarly, the product of sums is the product of all sums at which each sum is formatted by a single variables only. What does that mean? That means that this is an example of a product of sum, while this is not an example of product of sum. Why it's not an example product of sum? So each of the sums in the product of sum form is called the max term. Thus, the form is called product of max terms. So let me share with you how we can, in general, describe any function or any truth or convert any truth table to the standard format. So if I would like to write the format of the sum of a product on my truth table, what I have to do is to describe each possibility as a minterm and refer to the possibility by referring to the variable as its true format or at its negative format. In other words, if I would like to refer to 0, 0, 0, it should be equal, that minterm will be equal to x prime, y prime, z prime. And if I would like to refer to, let's suppose here, there's something that I'm not sharing it with you. I have here 0, 1, and 0. So that means that x should be at the negative, at the complement format, y should be at the true format, and z should be at the complement format. So that will be equal to x prime, y, and z, okay? And this basically represent what? M2, okay? So how many minterms I can write? It's basically depending on the number of possibilities on my truth table. So in general, an n variable of any functions, okay, will require 2 to the power n minterms and max terms. So let's suppose that here your function f has 4 variables, so a, b, c, and d. So in order to represent it on a truth table, you need 2 to the power 4, that means 16. So you will have 16 minterms where M0 can be described as A prime, B prime, C prime, and D prime. And M15 will be represented as A, B, C, D. Okay? So when it comes to the max term, what will happen is we will use the negative logic. So what does that mean? That means the 0 will represent here the high, the 0 will, will represent the high voltage, and the 1 will represent the low voltage, okay? So if I would like to write this as in terms of a max term, so this should be x plus y plus z, because those are what? Those are sums, then I will product them, whereas here those are products and then I will sum them, okay? So each minterm and max term max term represents exactly one combination row in the truth table. And after that, when I would like to write my functions, I will basically go and look where my function gives high. Here, let's suppose that I have a function g, and I would like to represent it in terms of the sum of the minterms. So I have to pay attention to here, and I have to pay attention to here, and I have to pay attention to here. So remember, guys, those are the minterm from 0, and this is the minterm the minterm 7. Okay, so basically the function g is high at minterm 3, m3, okay, as well as m6 and m7. So what I'm gonna do is I'm gonna sum those products, okay, because I will write the minterms in a product formats, okay. 3 can be rewritten as x prime y z, okay, and m6 can be written as x y z prime. m7 can be written as x, y, and z. So these I will sum them together, and as such, function g can be represented as this, okay? Another way of expressing the function in terms of the sum of product is you can say that this function is equal a sum of 3, 6, and 7, because we have m3, m6, and m7 at which the function is equal to 1. When it comes to the max term, we will do the opposite. We will follow the negative logic. Okay, so we will check at the truth table wherever the function is equal to 0, and then write the max terms, okay, and then we will multiply it with each others, okay. So the function g is equal to 0 at the max term m capital, the max term 0, where m0, in order to be rewritten, x equal to 0, so it's a negative logic, so it will be x itself plus not and it will be or, okay, plus y plus z, that is m0, and it's also like 0 when it is what, it's at m1, m capital 1, at m capital 2, and m capital 4, and m capital 5. So what's the description of m2? m2 can be written as x. Now why? Because it's 1 and I'm describing a max term, it's going to be that y prime, and this will be equal to z. So it will be x plus y prime plus z, okay? X plus, yeah, y prime plus z. So the whole thing can be rewritten as x plus y plus z for this m capital 1, x plus y plus z prime for m capital 0, and here it's m capital 1, and at m capital 2 as well. So m capital 2, it will be x plus y prime plus z, and at 4 it will be like x prime plus y plus z prime plus z, sorry, and at m5, which is x prime plus y plus z prime. So another way of writing the max term is what? Is following this symbol and then referring to the rows at which the function is equal to 0, which is at 0, 1, 2, 4, and 5. Okay, so as you can see, guys, you know, the max term will be the opposite with the min term, because the min term we were looking for 3, 6, and 7, and the remaining ones will for sure represent what? The okay, at the midterm we were looking at 3, 6, and 7, and at the max term we will be looking what are the missing here? we're missing 0, 1, 2, and then we're missing 4 and 5. Okay, so after that, since I was capable to write my function using the AND, OR, as well as the negation, I can implement it here. Okay, so this function will be implemented by multiple of ANDs, and at the end they will be OR. Okay, so I have X prime, so I have to negate it. Then Y and Z, they will be what? Just here I have Y, and here I have Z. That's for the first minterm. For the second minterm, I have here I have X, Y, Z prime. So I will take X as a true and add it to this AND. Then I will have Y and will add it as an input for this AND. And then I will have Z prime and will add it as an input for this AND. Okay. And similarly, I will apply the same thing with for the third term here, where I have all of them at the true format. Okay, as you can see, guys. And then we will OR it together. That is called the sum of a product. We are summing the products. Okay. When it comes to the product of sum, we will do the opposite. Okay, so what we will do first, we will OR all the terms. Then after that, we'll product them at the end with the AND. Okay, so that's it for today, guys. And I will see you live on Friday. Okay, have a nice day.